Welcome back to Next Gen Manufacturing Nexus. Today, we're diving into something you can't see, but it's everywhere. A force that shapes everything from the chips in your phone to the tallest buildings on Earth. We're talking about the invisible battle against vibration. So, let me ask you something. What in the world connects a skyscraper, a microchip, and a Formula One car? I mean, think about it. They couldn't be more different, right? They exist in totally separate worlds, on completely different scales, and yet, they all share one critical weakness. Yep, every single one of them is fighting a constant battle against a hidden enemy. An enemy that doesn't care how big you are, what you're made of, or what you're supposed to do. Its only goal, to shake things. To bits. So let's pull back the curtain and get a good look at this opponent. Welcome to Section 1, Vibration, the Hidden Enemy. Okay, so what is vibration? At its core, it's just a mechanical wobble, right? A shake. But in the world of engineering, oh man, it is so much more. It's an invisible force that can totally ruin the super tiny circuits on a microchip or, bring down an entire bridge. It is a silent, constant stress test happening all around us all the time. And here's where it gets really dangerous. Every single object, and I mean everything, has a natural frequency. Think of it like a musical note it loves to hum at. Now, if an outside vibration happens to hit that exact note, you get resonance, and that is a game changer. It's how a tiny, harmless little shake can suddenly amplify itself into a massive, destructive force. Resonance is the superweapon in vibration's arsenal. But here's the good news. Engineers don't back down from a fight. And for this particular bottle, they've come up with two main strategies, two totally different ways of thinking about how to fight back. You can think of it like this, the shield versus the counterpunch. On one hand, you've got passive isolation. That's the shield. It's all about using smart materials and designs to just absorb or block the vibration. Then you have active control. That's the counterpunch. It doesn't just block the hit, it sees it coming and throws an equal and opposite punch to cancel it out completely. Okay, let's dig into the shield first. Section 3, passive defense. The whole idea here is to soak up all that shaky energy before it can cause any real trouble, just by using the natural properties of certain materials. So what's in this passive toolkit? Well, you've got some stuff you'd probably recognize. Rubber pads, metal springs, even air isolators. Rubber, in particular, is a real favorite because it's just so good at bouncing back. But one of the coolest tools in the box is something called a viscoelastic layer. All right, picture a basic steel beam. If you hit it, it's going to vibrate, right? And that vibration just rings through it for a while. Now, that's not a huge deal if it's just a beam. But if it's part of a high-precision machine or the floor of a skyscraper, yeah, that's a problem. So here's the genius fix. Engineers create this kind of sandwich on the beam. They add what's called a constrained viscoelastic layer. It's got this gooey, energy-sucking material in the middle. So now when the beam tries to shake, that middle layer gets squished and stretched, and it literally turns the vibration energy into a tiny bit of heat. How cool is that? And the result? It's just... And the result? It's just a brilliantly simple, super effective shield. But sometimes a shield isn't enough. What if you need something to be absolutely perfectly still no matter what's shaking around it? Well, for that, you need to go on the offensive. You need a counterattack. And that brings us to active vibration control. This isn't about soaking up shakes. Nope. This is about creating a brand new, perfectly opposite shake to cancel the first one out entirely. You know how noise-canceling headphones work? It's exactly like that, but for physical movement. So how does it work? It's a super fast three-step dance. First, it senses the vibration with incredibly sensitive accelerometers. Second, it processes that signal. A little computer brain flips it completely upside down, a perfect 180-degree inverse. And third, it acts. Actuators jump into action and generate that exact opposite vibration, wiping the original one right off the map. Now, this might sound like overkill, but for ultra-precision work, it's a must. I'm talking about manufacturing semiconductor wafers. When you are etching lines that are nanometers wide, literally the vibration from someone walking down the hall can scrap an entire batch of chips. Active control creates this tiny bubble of perfect calm that makes all of modern manufacturing possible. Okay, now for my favorite part, let's shine a spotlight on one of the most elegant and frankly just awe-inspiring vibration solutions ever created, the Tuned Mass Damper, or TMD. So what is it? A TMD is actually pretty simple in concept. It's a giant weight connected to a building with springs and shock absorbers. The key is it's tuned to the building's own natural swaying frequency. So when the building starts to sway one way, the TMD sways the other way, out of sync, and gently pulls the building back to the middle. And the most famous one of all? You gotta see the one in the Taipei 101 skyscraper. It's a 660 metric ton steel ball hanging right in the middle of the building. And the effect is just huge. You can see it right here in the data. A TMD can knock down the peak vibration by almost 40%. What it's actually doing is really clever. It takes that one huge, dangerous resonance peak and splits it into two smaller, totally manageable ones. So it doesn't get rid of the energy, it just tames it. And once you know what to look for, you'll see these things everywhere. Seriously. They're in skyscrapers like Taipei 101, they've fixed the wobbly Millennium Bridge in London. You see those little dumbbell-looking things on power lines? Those are TMDs. They even put them in Formula One cars for a while and designed them for NASA's rockets. It's just a massively powerful and flexible idea. So, when you step back and look at it, this whole invisible war, this fight against vibration using both passive shields and active counterpunches, it's what makes our modern world work. It's what gives us the incredible precision for next-gen manufacturing, and it's what keeps the giant structures we rely on every single day safe and sound. And that leaves us with one last question to chew on. As our tools for creating perfect stillness get better and better, what new things will we be able to build? What kinds of structures or machines that seem impossible today will finally become stable enough to exist? What's next?